Hello everyone, and welcome to our presentation for Lab 2 SSI Circuits for eSEN 160 Fundamentals of Digital Systems. Here in the section we have the truth table given to us in the lab. Truth tables are very easy to read. Truth tables give us a way to interpret the results of different combinations of the inputs. We can also use a truth table to derive Boolean equations, which we'll now talk about how to derive a non-reduced Boolean equation from a truth table. Here is the non-reduced equation. As you may notice, there are 10 terms. That is because there are 10 true outputs. We have outlined them in the truth table with red. Each true output represents a single term in the equation. For example, the very last term for the equation is A0 and B0 and C0 and D0. That term is derived from the very top true output on the truth table. It is very simple to derive a non-reduced Boolean equation by simply taking each true output and writing out the inputs, then moving on to the next true input and repeating the same process. Once we get the non-reduced equation, we can also create the reduced version. From the non-reduced equation, we can use Boolean theorems to simplify the equation. Here, the reduced equation is C0 or B0 and D0. We found it a lot easier to derive the reduced equation using Carnot maps. A K-map is a pictorial method to minimize Boolean expressions without the use of Boolean algebra or manipulation. Basically, think of a K-map as another version of a truth table. On the right-hand side is a 4-variable K-map. The top section represents the variables A and B, while the left-hand section of the K-map represents the variables C and D, or the inputs C and D. The numbers representing the different values of the inputs. Filling out a K-map is very simple. For example, let's fill out the top left-hand corner of the K-map. In that box, it can be read as if A and B are 0 and C and D are 0. What is the output? As you can see from the truth table on the left-hand side, we can see that if A and B and C and D are 0, then the output is 1. Thus, we put a 1 on the top left-hand corner. You repeat this process until the whole entire K-map is finished. Here is the finished K-map. Next, we will talk about looping through the K-map and how we will use this method to derive the reduced Boolean equation. Looping through the K-map creates sets that will be used to derive the reduced equation. Here in the first loop is the first set, which is indicated by the blue. As you can see, a set is represented by many terms, which correspond to a row in the truth table. Here in the second loop, which is marked by green, we show the second set. This is where things get interesting. We'll now show you how to derive the reduced equation from a K-map using looping. Each set represents a term in the equation. Set 0 represents the first term, which is C0. Set 1 represents the second term, which is B0 and D0. Now you're probably asking, how did you come up with that? If we look at set 0, which is the blue, we want to find the variable that is not changing. In this case, inputs A, B, and D are changing throughout each true output, while variable C is not. C is the constant. It will always remain 0 or false throughout the whole entire loop. Thus, C0 is set 0. If we take a look at the next loop, we will see that the only non-changing inputs are B and D, which in this case, they are both always 0. Thus, set 1 is B0 and D0. Overall, to find the terms for a reduced Boolean equation, we find the non-changing inputs for each loop. Now we want to make sure that we are creating the sets or loops correctly, which is why we've included some of the rules. For example, when creating the loops, they must be done in multiples of 2, meaning that you can't have a group of 3 true outputs or 5 true outputs. It must be 1, 2, 4, 6, 8, and so forth. Another rule is that each true output can only be part of 2 loops. If you look at the top 2 corners of the K-map, you can see that those ones are being used by the first and second loop. If I were to highlight the top row, that would not be allowed since the 2 corner outputs are already being used. However, we can highlight the 2 middle row sections. Overall, we've listed hints to reduce an equation using a K-map.
Now, we're going to see how to implement this equation. As you can see here, we are using only 3 literals, C, B, and D. They are all inverted or negated, so we have a NOT gate with each one of them. And B and D, so we have an AND gate with B and D. And the output of that is ORed, so we have an OR gate here connecting it to C, and then we get the output according to the truth table. Now we're going to talk about a family of integrated circuits. chips, the 7400 series. This is an extended family of digital integrated circuits. Chips in this series include a variety of discrete logic chips, such as AND gates, NOR gates, as well as registers, decoders, and RAM units. So we have, for example, the 7404 that has a set of inverters inside. So we can take this chip and use the inverters that are in it. That is the same thing for the 7408 that has inside of it a set of AND gates. It also has 2 pins here for the power and a pin for the ground. In a real life situation, when we would use this integrated circuit, those pins would need to be connected. That's the same thing for the inverter, and the same thing for the OR gates or the 7432 integrated circuit. Now, we're going to do the same logic here. The difference is we're using a whole circuit just to use an individual gate, 1 or 2 here. So those pins or those gates inside of those chips, they go unused if we wanted to implement it at the gate level using those circuits. Now, let's talk first about functionality complete. So this is a set of gates that can implement any possible Boolean expression. So this set is not, and, or. To be able to create or represent any truth table using an AND gate, we have to make sure we can recreate OR, AND, and NOT gates. And actually, we can. To create, we connect the input in both pins, and this is going to reinvert the result. We can also recreate an AND gate using a NAND gate. It's pretty simple. We just invert the result using what we just learned in the previous slide. And to create an OR gate, we need to invert both inputs in this NAND gate. So we take those 2 NAND gates with both inputs connected, and we represent an OR gate. Now we can implement our logic. As we can see here, we have inverters in each of the pins or the inputs that we're going to use. This is the representation of an AND gate. AND gate followed by a NOT gate. And this is the representation of an OR gate. We have the NAND gate on the edge, and we have 2 inverters here. And we connect the pins as normal. But we are wasting a lot of gates here, and there is a way to reduce this circuit. So how do we do it? As you can see here, in this, we have the B and D, they're being inverted, and then we have these 2 gates that represent a NAND gate. And then we have this NAND gate or inverter part of the OR. We are negating it 2 times, so we don't need, so we can remove those 2 and have simply this OR gate right here, and we're going to get the same result. And that's the same thing with C. It's negated here, and then we invert it. It's inverted here, and then we invert it again. So it doesn't need to be inverted, so we connect it directly to the final AND gate, NAND gate, and we get this result, reduced version of this circuit using only NAND gates. Okay, this is the 7400 integrated circuit. This is the most popular circuit because it was implemented to be used on a TTL or transistor-transistor logic. In this logic, a NAND gate is the fastest. So the best performing circuits or digital systems utilize NAND gates, and the optimal implementation would never waste any of those gates inside those chips. So right here, we just would implement the reduced version we just did with this 7400 integrated circuit. As you can see here, you have 4 NAND gates that can be used. So let's compare what we got here. We started with this design that resembled our equation. We have the inverters, we have the AND gate, and we have the OR gate. Then we needed to translate that to use NAND gates. They are the most optimal gates to be used in this technology that we're going to implement, and we did it. And with visualizing this circuit, we noticed that we could simplify it and have the simplified version using only 4 of those gates. And this integrated circuit 7400 happens to have 4 gates. So we were able to implement it using it, NAND gates.
In conclusion, we hope that you have enjoyed this presentation and that you have learned more about Boolean algebra and equations, Carnot maps and truth tables, looping, and or and not circuits, NAND circuits, and finally integrated circuits.